Well, good evening, everyone. We're going to pick up where we left off last week. We're currently in Chapter 6 in the extra class. We did the first half last week, and second half will be this week. And on the screen, I've got the agenda for tonight. DSP and software is going to be in the software-defined radio is going to be in the first part, which is kind of an exciting part because virtually all radios being made today are SDRs, except for specialty things like QRP radios and so forth. But the major manufacturers are all making DSP radios or software-defined radios, or a combination thereof. Filters and impedance matching and power supplies have been around forever, but the pool committee thinks it's important that they make a lot of changes, I guess, between pool versions, so it was a little challenging getting this all ready, but these topics have been around for a while. And I think I mentioned last week that this is Gary and I are tied for Chapter 9 and Chapter 6 as being the longest chapters in the book. So a lot of meat here. We'll move right into it. To start off our discussion of software-defined radios, we'll chat a little bit about digital signal processing. And we've got a little section marked in red here. And this is some of the electronics behind how sequential sampling works. And the high-level overview is, well, here we've got a sine wave on the screen. And these red lines are samples. So every so often, we're going to take a snapshot, and we're going to convert the value of the sine wave into a number. It'll be stored digitally in binary, of course. But so we've got a sample here, one here, goes all the way through the 360-degree sine wave. Of course, speech is a lot more complicated. That's going to be bouncing all over the place. So there's a lot of advantages to processing signals digitally. You get better quality. A lot of the features can be implemented in software. Of course, software can be updated remotely, new versions. We do have a problem as human beings, though. If we're going to be operating the radio internally, digitally, our problem is we can't speak in ones and zeros, and we can't understand them. So we have to have someplace in the chain an analog to digital and a digital to analog conversion taking place so that it can interface with us lowly humans. There are several ways of doing sampling. We're going to be talking about several. And we'll just give us a very brief sidebar coming up here. There's nothing in the pool about this, but if you assume that we're counting numbers between 0 and 15, it's possible to look at those numbers in binary form. 0, of course, is all zeros. 15 is 1, 1, 1, 1. You could say that we have a bit depth of 4 bits here. There's four positions that can be set to 1 or 0. So in this case, we can represent any of 15 states, 16 if you count 0, as a binary number representing decimal numbers, which of course we understand a lot better because we have 10 fingers and 10 toes. And I had a link here if you're interested in learning more about binary numbers. I have a link there, you can dig into it. So some considerations regarding sampling. We've got the famous Nyquist sampling theorem, and that says that sampling needs to be at least twice the rate of the highest frequency component of the signal. So if you consider compact discs, for example, and the audio frequency range that they try to capture there goes up to 20,000 kilohertz, or 20,000 cycles per second. It has to be sampled at twice that rate in order for the audio to be reproduced faithfully. What normally happens is that most sampling is what they call oversampled, so it's much faster than that. Twice the rate is the absolute minimum. Now the problem, if you don't sample at least twice the highest frequency in the audio material that you're trying to sample, you'll get signals called aliases. They're false signals, and I'll show a diagram of how those are generated. So throughout the discussion on software-defined radios, we're going to see a number of cases where we're dealing with anti-aliasing filters to make sure that frequency ranges are constrained to a range that won't cause false signals. And then there's one more little trick here, also in the pool. A small amount of noise called dither may be added to the input signal to reduce quantization noise. Now, what is quantization noise, you might be wondering? Well, as we're sampling here, we are only sampling specific points. So it's going to wind up looking like a stair step. And those missing points in between the samples are generates a quantizing noise. I'll have another picture of that coming up. And a process, something called dither, is adding a small amount of noise to the input signal to help average some of that out. Now we'll take a look at what happens if we fail to sample at least 2 times the material frequency that we're trying to get. These little dots here, each little dot, they might be a little hard to see, but these are samples. And you'll see that the sampling is happening much slower than the sine wave that's trying to be sampled. So if you connect the dots, here's a dot that corresponds to this. Here's a dot, it corresponds down there. And you'll see that the recovered waveform, this waveform right here, has no resemblance whatsoever to the waveform that we were originally trying to sample. And that's because of aliasing. So this will generate an output, and this will be absolutely real, and it'll really confuse the electronics and your ears if it happens to be in the audible range. So this is a little picture of what that means and why we don't want it. Now in sampling and reconstruction, we saw this before. We saw the samples at each of these dots. And then when we reconstruct that waveform, because we're sampling at these discrete points, that's all that the waveform is going to know about. It doesn't know what's happening in between, but for a sine wave or for most speech material, this can be smoothed out. So if we use a filter, we can convert it back, but it's not going to be 100% faithful reproduction because of that quantizing noise. We're guessing between the stair steps. Another thing about square waves, or what we're seeing here, very sharp rise times, they're very rich in harmonics, which is another reason why we need to filter it out. So here we have a low-pass filter being applied to that jagged output. We want to convert that recovered waveform into something that's nice and smooth. And there's even a pool question. The purpose of a low-pass filter used at the output of a digital to analog converter is to remove spurious sampling artifacts from the output signal. Of course, you can imagine there'd be a lot of those spurious artifacts because of the fast rise times in the waveform here, the individual steps. Now we'll consider analog to digital conversion and how that works. And there's a fact here, number of bits determines resolution. I showed you in the sidebar when we were doing digital counting that we were basically dealing with four bits. And that's on this chart too, 4 bits. And what's happening, if you take 2 to the 4th power, we get 16 states. You might remember the chart had 0 plus 15 for a total of 16 steps or states. So number of bits, it's over here. And the number of bits being used is also called the resolution that's being applied to the waveform we're sampling. Also bit depth, same idea here, bits or bit depth. Also number of levels, okay? These are all just terms that kind of mean the same thing, steps and precision. So if you apply some of these words, with 10 bits of precision, we have a number that's equivalent to 2 to the 10th power, which works out to 1024. Now I've put a couple of these things in blue because there's 2 pool questions that relate to this. You can either multiply 2 times 2 times 2 and go the number of times of the exponent if you care to, or you can do this on your calculator. There's a function key there that will give it to you. But there will be a question that says how many states can be represented with a bit depth, or one of these words, I don't remember which one it was, of 8. 2 to the 8th is 256. It's another one that's a very confusing looking question, but when we talk through it, I'm pretty sure you'll get it, using 10 bits, which will allow us to resolve 1,024 steps in total. All right, right on to a pool question. How many different input levels can be encoded by an analog to digital converter with 8-bit resolution? If you want to do it on your calculator, it's 2 to the 8th power, or 256, and I'll demonstrate that just so that you'll know how to do it if you care to. Come over to the calculator cam, I'll turn it on, press clear. And there's a function here we haven't used before. I got to find it now.
Left.
Oh, here, right here, yeah. No, that's square root. We want, I did this before I came over here tonight. I'm still not seeing it.
Wasn't it X to the box?
Oh, X to the box. I'm looking for the shifted stuff. Okay, that's it. Thank you, Gary. I'm glad Gary's smarter than I am. So I'm going to do X to the box. We don't want the answer thing. We want, we're going to consider the case of 8 bits. Do 8, X to the box. No, I don't want to do that either.
2.
2, correct.
Clear it up. There you go.
Yeah, and 8. All right, well, sorry for that foolishness. So 2 to the 8th power, press enter, we get 256. So if we come back to the presentation, we did it. I was trying to make that easy for you and messed it all up. So.
But you say that when you make mistakes, you learn.
That's right, exactly, absolutely. All right, so here's the one that's tricky. But if we talk through it, I hope that it'll make sense. They're going to ask, what is the minimum number of bits required to sample a signal with a range of 1 volt at a resolution of 1 millivolt? So the first thing to consider is that there are 1,000 millivolts in a volt, okay? So we're going to need a bit depth that will give us at least 1,000 steps. That turns out to be 2 to the 10th, or 1024. So in order to handle this, we're going to need a bit depth of 10 bits. Minimum number of bits required to sample a signal with a range of 1 volt at a resolution of 1 millivolt. So we'll be able to count any number of millivolts between 0 and 1,000 with 10 bits, which would give us 1024. We don't need quite that many. So kind of hold that thought for now. We're going to see it again in a little bit. Here's another question that sounds a little confusing. What sets the minimum detectable signal level for direct sampling SDI receiver in the absence of atmospheric or thermal noise? Well, remember in the previous slide, we saw that that number, in this case we're using 1 volt and 1 millivolt. So what sets the minimum detectable signal level for direct sampling SDI receiver in the absence of atmospheric or thermal noise is the question. The reference voltage is the maximum voltage that you're expecting at the input of your receiver. And then we've got the sample width in bits. It's a specification of your radio. So if we were expecting a maximum input level at your receiver of 1 volt, that would be the reference voltage. And if we continue using the sample that we showed previously, that would, using 10 bits, 1024 steps, that would allow us to get down to a signal level, minimum detectable signal level of 1 millivolt. This is just as an example because, of course, weak signals are in microvolts, so it's much broader than this. but just trying to apply this concept to what we just learned. And you may have noticed if you've got an SDR that occasionally the OVR light might come on if there's a lot of strong signals. That's the overflow light, meaning that there's too much RF coming into the front of your radio and it can't handle it all. So in that case, you would have to crank in some attenuation. I've very rarely seen this on my radio, but it does happen. So quality, we were talking about the stair steps that come out of a digitally recovered waveform. So how would we measure that quality? Ideally, it should look exactly like the input waveform that was digitized. So reconstruction of the waveform is not perfect. There will be some distortion. And the way that they measure it is by measuring total harmonic distortion. Now, you may have heard of total harmonic distortion in terms of stereo specifications. That's a really big deal. They like your audio to be as clean as possible if you're listening to your favorite music. And it's down in tenths or even hundredths of a percent total harmonic distortion on the best equipment. That measurement is also used to measure the quality of an analog to digital converter. So analog input, we convert it to digital, then we convert it back to analog, digital to analog converter, and then we can measure the total harmonic distortion. If you want to know a little bit more about that, I put a link here for you. You can dig further. But the important thing is the blue text here. Now Fourier, a very, very interesting guy, and he goes back a ways. He goes back before we really had radio. French mathematician, Joseph Fourier, he died in 1830, and he was applying this to heat transfer in physics. But the same principles are used by us today in radio. So he proved or showed mathematically that a square wave is made up of a sine wave plus all of its odd harmonics. So basically any kind of a waveform you can dream up is some combination of sine waves all added together. Yeah, heat and vibration is what he was dealing with way back then. The math was pretty difficult, so somebody much later, it was 1965, came up with what's called a fast Fourier transform, or FFT, and that's the mathematical function that's used for doing things in our radios. I'll show you some examples coming up. This is the FFT, modified his math to make it a lot easier to use. And it converts signals from the time domain to the frequency domain. Time domain is what you would see on an oscilloscope. And frequency domain is what you would see on a spectrum analyzer. And we'll have some pictures of those coming up. So here's the gentleman. I don't know how they were taking pictures back then, but I guess they were. And this kind of tickled my funny bone. These are Fourier equations written on a T-shirt or a dress. I don't think the lady comes with the T-shirt, but this might be a Christmas present that you want to give your ham friends. You can also get Maxwell's equations on T-shirts if you wish. So time versus frequency domain. Here we've got an oscilloscope, and we've got kind of a funky looking sine wave here, but they tried. Give them credit for that. And if we look at the same signal in the frequency domain, that's a representation over here. And then what we have here, you can kind of see a square wave forming here. And what we're showing is that the odd harmonics, this is the fundamental, the third and fifth harmonic, if you add those all together, and this is a picture of the frequency domain over here, fundamental, third, fifth, seventh, etc., in the time domain, that it starts looking like a square wave, kind of proving Fourier's principles. So where do we see that today, you might be wondering? Why is any of this important? Well, have you ever seen anything that looks like this? This is a spectrum display on a modern radio. This happens to be an ICOM 7300. And this display is actually pretty useful because If you've got a radio that has this kind of a display, it normally also has a function where if you click on the display, it'll automatically tune the radio to that frequency. So here's a picture of single sideband. Of course, remember that single sideband is about 3 kilohertz. You see the wider signal here representing voice. And then over on CW, they look more like spikes, individual frequencies. And in contesting, I very much enjoyed this feature on my radio, which is an ICOM 7610, because if I see a strong signal here, all I have to do is click on it, and the radio will immediately tune to that frequency without having made it I don't need to touch any knobs. So in the good old days, you'd have to start at the bottom of the band and slowly tune up the band, listening for signals. But with a spectrum display, you can just click on anything that's strong, save yourself a ton of time. And of course, in contesting, rate is king. You want to make as many contacts as you can. So this is one example of FFT in action. Now we're going to get into some technical sounding terms. You remember mixers and local oscillators and output frequencies and all of that we've talked about before. Well, decimation is really the equivalent of doing that in software or numbers. So the function of decimation is reducing the effective sample rate by removing samples. So this is some of Kessler's material here. So in this case, there's a 14.300 megahertz signal coming in, sampled at 100 mega samples per second. And then this says local oscillator, but it's really a digital bit stream going on at 14 megahertz. The output going to be here. And then decimation, there's a block here that'll take, it'll just take one sample out of every 1,000. So that brings us down to an audio frequency. And radios digital signal processing deals much more effectively with lower bit rates. But we've got to get down to that in order to apply that technology. So the key is that decimation reduces the effective sample rate by removing samples. It's a little bit like analog mixer, but it's all done in the digital domain. Now here we've got our anti-aliasing term popping up again. In anti-aliasing, digital filter is required in a digital decimator to remove high-frequency signal components that would otherwise be reproduced as lower frequency components. Typically, when you're doing down conversion, like is shown here, some of the higher frequency bit rate is going to be sneaking through. So we can get rid of that by using an anti-aliasing filter so we won't confuse the next stage in the chain. So the key is that a digital filter is required at the output of a decimator. Otherwise you'll be generating, or you'll be putting things into the next stage of the radio that are going to cause aliasing issues. Just giving us high-level concepts here. If you want to really dig into this, if you want to make your brain smoke, Google on some of these terms. So here's a generic DSP, digital signal processing system. And it's someplace, we don't know what frequencies are involved here from the diagram, but we've got some kind of an analog signal coming in. We're going to convert that analog to digital with an analog to digital converter, get it into the digital domain. And then our DSP, digital signal processing electronics, is going to perform some kind of magic on it. And the magic is almost without, the sky's the limit, okay? We're talking about notch filters, bandpass filters, noise filters, modulation, demodulation, all of that can happen in DSP. And eventually, when we're done with that, let's say that we're we're demodulating single sideband, for example. Eventually, we want that to convert that back into something that we as humans can understand, and that's what the digital to analog converter does, analog signal out. So we can bring a signal in, do all kinds of magic on it, completely in software, all digitally, convert it back to audio, and then we can hear it. So this can happen any place in a radio. So what kind of information can be processed? Virtually anything. Speech, video, data. It's like a magic box. And we already mentioned these terms, analog to digital conversion coming in, digital to analog conversion. It's a human to machine interface, if you want to call it that. And we've got some really interesting things that happen. Digital, I'm thinking of FT8 right now, other digital modulation systems as well. The signal is buried in the noise. So if you were listening to this, you wouldn't even be able to tell that this signal was in there. We're showing a square wave here, but of course it's some kind of a modulated digital signal, completely buried in noise. But DSP, through various techniques, can actually pick out the signal that's hidden in the noise. That's one of the reasons that FT8 will work well below the noise. You can't even hear it, and it's decoding. So in a receiver, let's consider that now. I mentioned DSP could occur basically anywhere. In this case, we've got analog RF coming into the front end of our receiver. We've got an intermediate frequency, so there's some analog mixing going on here. And then we've got our digital signal processing, analog to digital, digital to analog to audio. I've got a Yaesu FT1200DX radio. Gary's got the same radio, I think. You still have it, right? Yep. And it does analog mixing in the front end, and then it gets down to a level where digital signal processing is better able to handle it, and it does all of its magic here. So the front end of the radio is analog. The decoding and signal processing is digital, and then back out. And the neat thing is that this portion, from the time that we convert it from analog to digital, all of this can be done in a computer. It doesn't need to be done in a radio necessarily. So we looked a little bit at the aliasing issue and mentioned decimation. We mentioned that decimation reduces data rates by removing samples. We want to reduce the data speed because digital processing will normally run at a much lower rate than what's coming in RF-wise. Instead of 14 megahertz, we might want to be working at just a couple of megahertz. And this is also called down converting, a little bit like analog mixing coming to an intermediate frequency. And it requires an anti-aliasing filter to remove high frequency components. And this piece of it's kind of a review of what we talked about. And then, okay, so that's a way that we can reduce a data rate. There's no pull questions on interpolation, but that's another key concept, an extremely important part of a software-defined radio. This increases data rates by adding samples. Remember with decimation, we were removing samples? Well, we can add samples, also called upconverting. And we up convert to the point where we've got the output of a stage earlier in the radio, in the transmit chain, and we want to get it up to the carrier frequency. Well, interpolation is how they do that, also called up converting. And when we see a block diagram of a software-defined radio, hopefully these things will start falling into place. It's ways of manipulating data streams. Here we've got a picture of a low-pass filter. I think I've got a bigger image of it there. And you might recall from our discussion, well, we haven't really gotten into filters yet. That'll be later this evening. But a filter will normally have a cutoff point, which is 3 dB power-wise that's below what's coming in. So that this is the bandwidth. In the case of our anti-aliasing filters, the same concept applies. Back up here. So low-pass filter. Okay, prior to sampling, before we do our digital, our analog to digital conversion, also used in decimation, we want to make sure that the signals coming into our, I'll say the radio in this case, signals coming into the radio don't exceed 2 times the sampling rate, or we're going to have that aliasing problem. So a low-pass filter will keep those higher frequencies from coming in. So if we're wanting to listen to 20 meters, you don't want 15 and 10 interfering with the output. In this application, again, it's an anti-aliasing filter. We'll see these low-pass filters used all over the place in digital electronics. So we've seen this. Now, after digital to analog conversion, we want to remove the spurious outputs from the digital processing. Those recovered waveform will look like a stair step, so we'll want to use a low-pass filter to turn that back into a sine wave, or speech that can be understood. Smooths out the waveform, and this is part of a reconstruction filter. So low-pass filters, you'll see them as anti-aliasing filters and smoothing filters on the outputs. All over the place. Here's our picture again. Just a little link if you want to learn more. And we saw this before. After digital to analog, we want to remove the harmonics and spurious outputs and smooth the waveform. Just reviewing and reinforcing. And right into some questions. Well, that's some pretty complicated stuff we touched on. Let's see if we can answer some questions. How frequently must an analog signal be sampled to be accurately reproduced? Easy to get this one backwards. So somebody can unmute and give us a guess.
Beta.
Yeah, it is beta, at least twice the rate of the highest frequency component of the signal, which is the Nyquist limit. Typically, it's much more than that, but it has to be at least twice. What is the minimum number of bits required to sample a signal with a range of 1 millivolt at a resolution, 1 volt at a resolution of 1 millivolt?
The delta.
Yeah, delta, that's 10 bits, or 1024. Correct. That was the one of the two pool questions I said would be showing up. What sets the minimum detectable signal level for a direct sampling software defined receiver in the absence of atmospheric or thermal noise?
Adding dither.
Baker.
It is Baker. Reference voltage level, which is the maximum you expect to be coming in, and the sample width in bits, which is hopefully the the maximum sensitivity of the receiver. Correct. What is dither with respect to analog to digital converters?
Baker.
It is Baker. Yep. A small amount of noise added to the input signal to reduce quantization noise. And quantization noise is, of course, that stair-step effect with the rigid harmonics. Okay, here's the other bit number question I mentioned. How many different input levels can be encoded by an analog to digital converter with 8 bits of resolution?
Delta.
Delta.
256, which is 2 to the 8th power. I'll never forget that after messing it up on the calculator. What is the purpose of a low-pass filter used at the output of an analog to digital converter?
Digital to analog.
Yeah, that's even better. What is the purpose of a low-pass filter used at the output of a digital to analog converter? Thank you, Gary.
Charlie.
Charlie, remove the spurious sampling artifacts from the output signal. Smooth out those stair steps. Which of the following is a measure of the quality of an analog to digital converter?
Alpha.
Total harmonic distortion, alpha, correct. What function is performed by a fast Fourier transform? See if we remember the words.
Charlie.
It is Charlie, converting signals from the time domain to the frequency domain, like the spectrum display on a modern radio. What is the function of decimation?
Bravo. Baker.
Right, reducing the effective sample rate by removing samples. So you wind up with a lower bit rate out of the decimator. Why is an anti-aliasing filter required in a decimator?
Alpha.
Charlie.
Alpha.
But it is alpha. It removes the high frequency signal components that would otherwise be reproduced at lower frequency components when they're passed along to the next stage, for example. And then we'll move right into software-defined radio. This is really, really exciting stuff. So here, I've got a couple pictures here. Here's an ICOM 7300. And here's a Flex 6600. And that's your radio, isn't it, Carrie? Yep.
Yeah.
Yep. So these are some radios, and SDRs are sometimes called SDRs with knobs. Okay, the 7300 has got knobs on it. Gary's radio doesn't have any knobs on it. So his interface is his computer. Remember we said earlier that a lot of that digital signal processing can happen in the computer. Well, there's this one and the Anon series of radios that have no knobs on them. So SDR is a radio whose functionality can be altered by software. That's pretty cool because new features can be added to the radio without changing hardware or adding modules, hardware modules. Replaces traditional analog circuits with digital signal processing. And we talked about knobs and no knobs. So here's a picture. Now the ICOM 7300 and other ICOMs that happen to be SDRs with knobs, they are true SDRs as well. So you can buy software that will actually put all of the radio controls on your computer screen. This is ICOM's version here, but there's at least 2 other software packages that you can buy. They're only about $50 that will allow you to control that radio completely with software. Of course, that gives you options to do things remote control. You can't get to the knobs, but you can get to this. So looking now at a block diagram of a software-defined radio, and we're going to break this down in a little bit more detail. We're only going to be covering the high points, of course. We've got a microphone over here. So this is our transmit chain. And then we've got a speaker over here. So this is our receive chain. And a bunch of the terms we've talked about are going to be coming up here again. We haven't talked about I and Q signals yet, but we will. And in this case, we're digital all the way through. From the antenna, we're actually sampling it directly, going directly into the digital domain all the way through to the speaker. Well, we have to do digital analog before we hit the speaker. So in this case, it's a radio that's completely software defined. Okay, breaking this down a little bit further, some terms that we've seen. And this, if this is hard to read, this is on page 6-31 in your book. So if you're having difficulty here or want something that's a little bit easier to see, feel free to turn that to that page. So why SDR? All right, I'll give you some reasons. Almost any kind of a signal can be processed. Modulated, demodulated, filters, frequency synthesis. Functionality may be altered in software. New features or improvements. Achieves the magic of DSP we just discussed. And a really big one, which I think has influenced the manufacturers to go this way, the parts count is lower. You don't have coils and capacitors, and you have many, many fewer parts. So lower parts count and cheaper. Of course, you'd think that would be reflected in the price of the radio, but not yet. Not yet. I think we're paying for the technology that's inside. So we're going to have a couple of phases in this discussion. We'll show the concepts, and then we'll dig into a little bit more. And generally speaking, the DSP circuitry quite often can't run at carrier frequencies, so we have to do some down conversion. In my 7610, for example, most of the DSP happens at 2 megahertz, even though it is directly converted to digital right at the antenna. To do that, we have what are called down converters and up converters, receive and transmit. So we're going to show an overview and then move on to this I and Q technology. There's a few little blocks here that we've talked about already. Remember, we've got a reconstruction filter. We've talked about that. Something called interpolation, decimation. Trying to tie some of this together for us. So considering the transmit path, we've got DSP here, and somehow there's some magic that gives us a bit stream with the audio using I and Q signals, which we're coming to. We're then going to interpolate. This is running at a lower data rate over here, maybe 2 megasamples per second. We're going to interpolate to raise that. NCO is a numerically controlled oscillator. We're going to take our 90-degree phase shifted signals, again, which we're coming to, then convert it up, reconstruction filter, power amplifier, and out. So this is the transmit path. The receive path goes the opposite way. We're going to switch our TR relay to the receive side. We're going to immediately, right at the antenna, just right into the radio, we're going to digitize what's coming in. We see some automatic gain control electronics here, help avoid overdrive. And this is just working in the opposite way, except instead of interpolating to get up to a carrier frequency, we're going to do digital down conversion, DDC, with a decimator to bring the data rate down to what the digital signal processing circuitry can understand. And the output of that, after it's decoded, demodulated, whatever, filtered, is converted from digital analog back to something we can understand in our ear, the speaker. So that's the receive path. And I think I'm repeating this on the next slide as well, but direct sampling in software-defined radios, the incoming RF is digitized by an analog to digital converter without being mixed with a local oscillator signal. And that's meaningful because we have no analog mixing going on. We convert the incoming signal, we sample it immediately at the RF frequency. We don't have a local oscillator and a mixer in an intermediate frequency chain. Put a picture here of an SDR receiver. Used to, the RSP1A has been upgraded to the RSP1B. So here's a picture. It's a fully capable, very capable receiver actually for, I think it's $139 now at one of the ham radio outlet actually. So if you want to know a little bit more about that, or you want to play with a DSP receiver and you're not ready to go to a transceiver yet, this is a good option. Give you a spectrum display for a radio that might not have that capability. Now sample rate, I think we touched on this, determines the maximum received bandwidth. No, actually we didn't. Determines the maximum received bandwidth of a direct conversion SDR, software-defined radio. In your world, Gary, those are called slices, I think, aren't they? In
Yeah.
the flex radio. Yep. Determines how much bandwidth you can see. Most of the HF bands on my radio, I can see the entire band if I want to. You can adjust the lenses, so to speak, so you can zero in on the part of the band that you're interested in. But the sample rate determines the maximum received bandwidth of a direct conversion SDR. It's how
And I'll
much-
just say the flex radios use at the input, depending on the model, 1 or 2 what they call spectral capture units, or SCUs. And those are sampling at really ultra high frequencies because they're sampling the entire RF spectrum. And in many cases you can see multiple bands on the displays. So you can imagine the rate that they're having to sample those.
Yeah. Another sidelight that just came to mind from what Gary just said, some of the big contests, the contest sponsors are actually using technology like that to listen to every signal on the band, and then it's recorded. So they can catch people that are lying or violating the rules and so forth. So they can capture an entire 24-hour contest period for 20 meters, for example, and go back and look at any part of it, every signal that happened that they could hear. Just amazing technology. So there are a few more concepts of software-defined radio. I mentioned that most signal processing happens at a lower speed than what comes in at the front end of the radio. So there's a couple of techniques. Two of them are mentioned in the pool. One is called flash conversion. It's runs at very high speeds and allows digitizing high frequencies. And remember when we talked about comparators, when we were talking about op amps? I think that was last week. Well, that's what's happening here. They're checking signal levels, and if it's between A and B, it'll flip the output of an op amp and actually be able to decode. And this is a diagram of a 2-bit analog to digital converter, flash converter. Wikipedia's got some mind-bending articles on both of these technologies if you want to learn more about it. The other one is called successive approximation, another type of analog to digital conversion. The block diagram of how it's working in an article if you want to learn more. This is a KX3 radio. It also is an SDR. I have one of these. I use it for summits on the air, compact little QRP radio, but inside is a full-blown SDR. Now we're going to get into the magic of I and Q. I means in phase, quadrature means a signal that's shifted by 90 degrees. All kinds of magic comes out of this. And the mathematics is mind-blowing. I read through a little bit of it and said, no, I'm going to let the manufacturers figure that out. I don't want to understand it. I'm just happy to use it. So it's mathematical processing of these two signals that are shifted by 90 degrees. And then there's a special mathematical function called a Hilbert transform. That's the math function that will create digital, it's a digital signal processing filter used to generate an SSB signal directly. So no more generation, AM signal, double balance mixer, filter out one of the sidebands. This will generate it directly using the Hilbert transform. So this is this would also be called the phasing method. This is also the phasing method, just a little bit more. SSB may be generated by combining signals with a quadrature phase relationship. Some words you'll need to remember. And going back the other way, FFT technology will take the I and Q signals and recover the baseband modulation information for us. We've got mathematics at the bottom, mind-blowing stuff. So here's Mr. Hilbert, all right? Well, he was around when we had radio, okay? It was the early 1900s, a German mathematician. You can go to sleep here for a minute if you want, but I'll draw some parallels to something we've talked about. Remember when we were talking about the imaginary signals and real signals with complex impedance? Well, the same thing is happening with I and Q signals. The in phase is on the x-axis, or the real axis. The imaginary axis is the quadrature signal, shifted by 90 degrees. So they use the same kind of math. We saw it in complex impedance. It's also used I and Q math in software-defined radios. You don't need to understand all of this. So a little bit more now. In this case, we're going to be focusing on the I and Q signals. So I've blocked those out in red. We saw the up conversion and down conversion previously. So everything is happening in software. Everything's happening digitally. So this is what we saw before, the digital up conversion, reconstruction filter, power amplifier, and coming back the other way. So the output of these input and output are those I and Q signals. So again, we just barely touched on that. I and Q just think 90-degree phase shift, and then they do all kinds of magic in math to do all of those wonderful things, like filters and modulation and demodulation and all of that. So what is meant by direct sampling in software-defined radios?
Charlie.
It is Charlie. Incoming RF is digitized by an A to D converter without being mixed with a local oscillator signal. What aspect of receiver analog to digital conversion determines the maximum received bandwidth of a direct sampling software-defined radio?
Alpha.
It is alpha, the sampling rate. There's some other things that are tempting here, like this one, but it is sampling rate. The faster you can sample, the more stuff you can get. Which of the following is a type of analog to digital conversion? We talked about 3, I think. And one of
Alpha.
them- Alpha, yeah, successive approximation is one of them. Why are direct or flash conversion analog to digital converters used for a software-defined radio?
Charlie.
Charlie, yep. The front end of the radio where the RF is coming in, very high speed, allows digitizing those high frequencies. What type of digital signal processing filter is used to generate a single sideband signal?
Charlie.
Yep, Charlie, the Hilbert transform. I hope he got paid a lot of money. What method generates an SSB signal using digital signal processing?
Delta.
It is delta. Signals are combined in quadrature phase relationship, INQ magic. All right, that was a very high-speed walk through digital, or through software-defined radios and digital signal processing. But we had a lot of right answers, so thanks everyone for picking up on that. Now, filters and impedance matching this has been around for quite a while. But it's still fundamental to ham radio. So here's, I think, Kessler's picture of a filter. So you can see from the coffee filter here that you put the coffee inside the filter and you get clean coffee coming out of it. All of the gunk stays inside the filter. A very direct parallel to radio here. So we're going to talk about passive filters and active filters. Passive filters don't require any power. They use capacitors, inductors, resistors. We've got crystal filters, mechanical or Collins filters you might have heard of, cavity filters that are used for repeaters. And one characteristic of passive filters is they always have some insertion loss. Because they're passive, they have nothing powering them. So they can work their magic, but there's going to be less signal coming out of a passive filter than what's going in. Active filters will have an amplifying device built in, and they'll make up for insertion loss. They might even have gain. Here's a picture of a mechanical filter over here. And I thank the pool committee for making this subject a lot easier this time around. A crystal lattice filter is a filter for low-level signals made using quartz crystals. So here's one. This is actually an image from our license manual. It's what they call a half lattice filter. Don't really need to know how all of this stuff works, but there's a couple of crystals in there that create a filter with a very, very sharp output, very narrow pass band. Now it says low level. This isn't something we're going to be filtering transmit signals. We won't be putting watts through these. We'll be putting in microwatts. The relative frequencies of each crystal, two shown here, will determine the bandwidth and response shape of that filter. So here's a couple of flavors here. You might see the term ladder filter and lattice filter. For our purposes, the only thing that shows up in the pool is the word lattice. But there are a couple of different, it all comes down to how the crystals are combined in the circuit. And there's an article here if you care to learn more. And then something new in this pool is the helical filter. You may, if you like taking radios apart, like I do for VHF and UHF, sometimes you'll see these. The cans are opened up in this case. They're frequently used as a bandpass or notch filter in VHF and UHF. Now these are cavity filters. If you've ever been to an antenna site where there's 2-meter repeaters and other kinds of repeaters, you've probably seen these cans in there. These are cavity filters. They have an input and an output loop. Then the cavity and the resonator inside, there's a knob here that the plunger goes up and down, adjust the length of the resonator, and these are extremely sharp RF filters. Here's some internal pictures, and you'll see these commonly used in 2 meter band repeaters, repeater duplexers. And the purpose of the duplexer is, of course, so you can receive at the same time you're transmitting without hurting the receive input frequency. This is what filters those two out from each other. So there's all kinds of classifications of filters. Here's another helical resonator. We've got low pass, passes the frequencies below the cutoff frequency. We've got high pass, band stop or notch, all kinds of applications for these things. And here we're talking in the analog domain. These can be done digitally as well, but you don't need all of this hardware to do it. And the cutoff frequencies for a filter are defined as 6 dB below the maximum. That would be the voltage. So here's some graphs, and Kessler had some nice diagrams of this as well. Low pass passes the pass band, so lower frequencies. And then we've got the stop band. You don't hear anything above that. So low pass, you hear the low frequencies. High pass, you hear the high frequencies. If you take two of these and put them side by side, bring them in next together, you can have a notch. If you spread them apart, you can have a pass band. So these are all things that you can do using combinations of these kinds of filters to achieve these frequency responses. Now, shape factor, this is an important concept. We mentioned that there's a point that they're going to be talking voltage here, so 6 dB down in voltage, which would be half. So here's signals happily passing through the pass band in a low-pass filter. At some point, the frequency is going to get high enough where the filter is going to start rolling it off. When it gets down to the 6 dB point, that's considered the cutoff. And then the distance between 6 dB and way down here, notice how far the signal is down, between 6 and 60 dB, is referred to as the shape factor. A shape factor of 1, in other words, straight line going down, would be absolute perfection. That would also be referred to as a brick wall filter. With digital filters, you can actually approach that level of selectivity. It's amazing. So in context of the pool questions, shape factor measures a receiving filter's ability to reject signals in adjacent channels. So you want to hear this, you don't want to hear this. So the shape factor is kind of a measure of quality or selectivity, if you will. Design definitions. We've got phase response. Now it's possible that we're just filtering out individual signals, but we can also be affecting phase in a filter, because when we're dealing with coils and capacitors, we got reactance effects going on, which affects phase. And a linear response would indicate smooth or no ripple as the frequency changes. And nonlinear response in filters, a lot of the digital modes hate that. They don't want to see nonlinear response in a filter. It'll really hurt them. Filter ringing is, I don't know if you've ever narrowed a filter in a radio and got narrower and narrower, and sometimes it'll just start ringing. Like listening to CW, the CW elements are there, but the filter wants to oscillate and just keep right on going. That's called ringing. Another parallel to that, or analogy, would be like tapping a wine glass, and you slowly hear the vibration fade out. So that's something that's kind of comes with analog filters. And here's filter types. 2 of them appear in the pool. These have been around for a long, long time, early 1900s. We got 3 flavors we'll talk about. Butterworth, in its characteristics, very smooth pass band and stop band, but a fairly crummy skirt, if you want to call it that. But it's very smooth. So butter is smooth. All right, but there's no pool question there, so I can't help you with that. Chebyshev, notice it's got a much sharper skirt. So it's got ripple in the passband, some little bumps, very sharp cutoff. So why would you want to use one versus another? Well, it all depends on the application, what you're trying to accomplish. Then elliptical is extremely sharp cutoff. Notice it's almost vertical, but it has notches in both the stop band and in the pass band. So I kind of think of elliptical, if you draw an ellipse, you know, very narrow ellipses across the screen here, that reminds me it's an elliptical filter. Butterworth is very smooth. Chebyshev is kind of in between the two. Take a second to absorb the blue text. Crystal filters are amazing. A lot of uses to sharply filter. When we have analog mixers, you want to get the intermediate frequency and only the intermediate frequency to pass through the rest and to be amplified in the rest of the radio. So that's a place where you can see them. Sometimes you can, in older radios, you can actually get different filter kits for given different bandwidths for sideband or CW, for example. Lattice filters are typically made of quartz crystals, very narrow bandwidth, steep response. And of course, it's determined by the crystal frequency. You might have heard of a Jones filter in the good old days. It's a special type of crystal lattice filter. Also used in single sideband transmitters to filter out the unwanted sideband. So they kind of show up all over the place. And here's a picture of a very narrow passband. So we've got a signal source, maybe an intermediate frequency and a receiver. Quartz crystal will only allow a very narrow bandwidth to get through. Some pictures. I showed you some of these last week as well. So those are passive filters, coils, capacitors, crystals. They don't require any power, but they filter excellently. They have some insertion loss. Active filters are powered. So we have a case of an op amp here. This is an active low-pass filter. We see there's a capacitor in the feedback loop. They can be built without inductors. It's a combination of capacitors and resistors. Typically no insertion loss and can even have some gain. Usually built with op amps, and of course op amps don't run at high frequencies, so audio frequencies may be up to 10 to 100 kilohertz, if that. And gain and frequency determined by the feedback elements in the loop, external capacitance and resistance. Best suited for audio filtering. Mentioned that op amps are typically lower frequency devices. They're cheap. And here's a little technical tidbit. You don't want an op amp to go into oscillation, or you don't want a filter to be ringing to continue giving you signal after the signal's gone away. Preventing op amp ringing and audio instability in an op amp filter, if you restrict both the gain, now the gain is like the volume control on a public address amplifier. If you turn the amplifier down, the feedback will stop. So we'll restrict the gain. And if you restrict the Q, now Q, remember, that's the sharpness or selectivity of the feedback loop in an oscillator. And if that's extremely sharp, it's very easy for the filter to ring at that frequency. So if we can restrict both gain and Q, we can minimize op amp ringing. And here's just a picture of how one such circuit is implemented. Active, this is a bandpass filter. We've got capacitors and resistors in the feedback loop of the op amp that make it act as a filter. Do these exam questions and then we'll take a break. All right, which of the following is most frequently used as a bandpass or notch filter in VHF and UHF transceivers? Let's see if anybody remembers.
Bravo.
It is Bravo. Yes, the helical filter. We didn't talk about any of the rest of these yet. Which of the following filters would be used in a 2 meter band repeater duplexer?
Baker.
Yep. 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 Cavity filter. Which filter type has ripple in the pass band and a sharp cutoff?
Delta.
Delta.
Correct. Butterworth was very smooth. The only other one that they gave us was the Chevy Chev, so that was relatively easy. What are the characteristics of an elliptical filter?
Charlie.
Yes, extremely sharp cutoff with one or more notches in the stop band. Which of the following measures a filter's ability to reject signals in adjacent channels?
Charlie. Charlie.
That's the shape factor, Charlie. Yep. What is a crystal lattice filter?
Delta.
Delta, a filter for low-level signals made using quartz crystals. Yes. How can unwanted ringing in an audio and audio instability be prevented in an op-amp audio filter?
Alpha.
Alpha.
Yep, restrict both gain and Q, alpha. All right, now with this, we're going to go into filters and impedance matching after the break. So you can do whatever you like to do for 5 minutes, but please come back. We've got more fun things to do. Thank you. after a break. Hopefully everybody did something fun or get your mind off this for a few minutes. Now we're going to get into filters and impedance matching, something else that's just critical to ham radio. So here's a real simplified view of noise reduction. We've got noise reduction filters, we've got noise, and we've got signal. We want to let the signal through, but not the noise. So this would be an example of an adaptive signal filter. It lets some stuff through and won't let other stuff through. Very much like a coffee filter. You can see that parallel here. So in general, the digital filters use delay elements in series with taps between elements. And I found a picture here that I thought was really helpful. So here's an incoming data stream. And we've got T1, that's tap number 1. It's the raw data stream itself. And then we've got a delay here. And then something coming off that delay called tap 2. So we've got 3 different delays going here. So we've got 4 different signals all coming in and being summed to a different, to varying degrees of strength and showing up at the output. So that's the concept of a digital filter. This is just one kind. There's 2 kinds. Now the function of taps is to provide incremental signal delays for filter algorithms. So here we see those filters, or the delays. These are delays. And the taps pick up those delays, the original signal plus any of 3 delayed ones over here, all summed to different levels of signal output. So the mixing of tap outputs determines the performance, and if you want sharper signal response, more taps. So you get better selectivity going from 1 to 2, even more with 3. The only slight downside, well, it could be more than slight, with digital filters is you wind up with some delays, some timing errors that can creep in. So there's 2 flavors that they talk about for digital filters, the FIR and the IIR. FIR is finite impulse response. This is the picture I showed in the previous slide. And one of its characteristics is that it can delay all frequency components of a signal by the same amount. There's a finite decay time. So when the bit stream gets all the way through the 3rd one, well, it's gone. Something else has come in, so that there's no ringing at all. Now the infinite impulse response, this is more like an analog filter or tapping a wine glass. Behaves like an analog filter, infinite decay time. And the reason for that, we've got our delays going on here, but we also have some feedback loops that are coming back in and getting summed. So we're feeding some of the output back into the input, and that's what makes it infinite. In theory, it never stops. Okay, so it's very much like an analog filter, but in as practical case, they do quickly die out. So these are the 2 flavors: finite, infinite, finite impulse response, infinite impulse response. So what is an impulse, you might be wondering? That's like if you just apply a very brief signal to it, like a little spike, a tiny little square wave, and then watch what happens on the output. I'm going to get into a little bit more detail here. Here's the finite impulse response filter. We see delay, delay, delay. This is a 4-tap filter. How come it's 4 taps? I only see 3. Well, 1 is the input signal itself. So we've got the input signal, delay 1, delay 2, delay 3, 4-tap filter, finite impulse response filter, X, very similar to an analog filter. And the levels can all be controlled here. That affects its shape, its selectivity, all of those parameters. The infinite impulse response, here we've got a 3 feed forward taps, 1, 2, 3, we're feeding the input signal forward, and 2 feedback loops. Well, here's 1, delay and summing, and here's the other feedback loop. So this is what makes it act more like an analog filter. There's a concept called adaptive processing. That's like if you want to be able to hear signals, a single sideband sound, but you don't want to hear all the noise. So the software can recognize and adapt to different signals and conditions. No tuning requirement, sort of like the noise reduction on your modern transceiver. An adaptive filter used to remove unwanted noise from a received single sideband signal. Filter that's very smart about doing that. And with digital filters, you can build filters that are virtually impossible with hardware. I mentioned the brick wall filters. You can approach a shape factor of 1 with a digital signal filter. That was fast. Okay. E7FO2. What kind of digital signal processing audio filter is used to remove unwanted noise from a received single sideband signal?
Alpha.
That's our adaptive filter. Which of the following is generally true of finite infinite response filters?
Impulse.
Impulse filters. Yes. My eyes and my brain aren't always connected.
Alpha.
It is alpha. I don't remember if we emphasized that, but that's true because there aren't any feedback elements going on there. We're not affecting, or in the case of the finite impulse response filter, it has all of the frequencies in the output that are coming in on the input. What is the function of taps in a digital signal processing filter?
Delta.
Delta, provide incremental signal delays for filter algorithms. Which of the following would allow a digital signal processing filter to create a sharper filter response?
Baker.
Baker, more taps. Yes. Right on to impedance matching. All right. This we see all over the place in ham radio, especially between transmitters and antennas that may have different impedances. If source and load impedances are not equal, an impedance matching network is needed. Otherwise, you won't transfer the maximum amount of power to your antenna that you want. So how does this, if you have an impedance matching network, and I'm showing one here, very simple L filter. So how do we transform, how an impedance matching circuit transforms complex impedance into a resistive impedance? This is all combined in one question, but there's two elements. It cancels the reactive portion of the load impedance. Remember we had complex impedances we talked about? Well, you want to cancel out the J factor and then transform the resistive component into the desired value. So your transmitter might be 50 ohms, your antenna might be 200 ohms. You can get a combination here in a matching network that will make everything happy.
At one frequency.
At one frequency, yes, correct. Yeah, absolutely correct. So for transmitters, 50 ohm output, 50 ohm transmission line, 50 ohm antenna. That should have put a big smiley face here. Maximum power transfer occurs when all elements have equal impedance. But that's rarely the case. Most antennas don't have a one-to-one SWR. So where do you put this stuff? Well, here's the wall of your shack. Here's outside, here's inside. Typically your SWR meter, if you use one, it's going to be inside. The tuner is typically inside, and then the transmission line and antenna. So the antenna tuner is acting on the antenna system, being the transmission line and antenna. It is possible to put a tuner at the antenna, but then you have to it's up in the air someplace, and you have to have a control cable for it to work. This is the typical way that you'll see it. Here's a visual of one kind of antenna tuner. You see capacitors and an inductor. So they're putting these reactive elements in there so you can do the tuning. So we've got high pass and low pass filters, and I'm going to give you some memory tricks to help you figure out which one is which, because there's some questions that are they'll be very tricky if you don't grab some of these concepts, the little memory tricks I'm going to share. So capacitors pass in this case, we've got a filter with it. This is a series element here. We've got your transmitter, your antenna. In series with that is a capacitor. So capacitors pass high frequencies best. High pass filters have a capacitor in series. Just the opposite, if you have an inductor in series with the load, it's going to be a low pass filter. So all kinds of configurations. This is called a pi, and you can kind of see the pi character in the shape of the filter or the circuit. Here's a T, so this looks like a T. And here's a pi that didn't turn out right. Pretend that this doesn't exist. I know what happened. I shifted it. I covered this up, and then I moved this over to give me more room. So this piece doesn't exist in an L filter. So here's the memory tricks. I just thought this up this week. Kind of stupid, but it really helps remember which one is which. So first of all, look at the series element. Okay, the series element here is an inductor. The series element here is the capacitor. What I mean by series? Well, here's the transmitter, here's the load. We're going to have an inductor in series with the load. We're going to have capacitance in series with the load. So look at the series elements first. Secondly, consider a capacitor as a hurdle, a high jump hurdle. Okay, so here we've got a young lady doing a high jump. Okay, so here's the hurdle. A capacitor is a hurdle, and you must jump over the hurdle, so you have a high pass. I told you this was kind of stupid, but if you can visualize this, it'll help you get 2 or 3 pool questions right. All right, well, what about the other case? Well, the inductor, think of it as a limbo bar. So here's an inductor. We're going to have to go underneath. So an inductor, limbo bar, must go under. We've got a low pass filter. So if you can think of a better way to remember that, have at it, but this worked for me. And if you can remember this, there's 2 or 3 pool questions that you're going to be able to answer. And here's a pi L. Here's a pi with an inductor on the output. So these 2 components form an L. So this is what a pi L is. Okay, so more on pi and pi L networks. Now this is the one that's going to be really hard to answer if you don't have a picture of what we just shared. So a low pass pi. First of all, if it's low pass, it's going to have an inductor as the series element, right? So whatever the series element is, the parallel or shunt elements are going to be the other flavor. So if you've got a low pass filter with an inductor in series, the input and output components are going to be capacitors. So low pass pi, it's a capacitor connected between the input and ground, another capacitor connected between the output and ground, and an inductor, and an inductor is connected between the input and output. So the series device is an inductor, low pass, go under the limbo bar. A pi L is a pi network with an additional inductor on the output. Show that here in a second. Right here. Purpose of adding an inductor to a pi network is to create a pi L network, this thing here, with greater harmonic suppression. So if you want to have a matching network that will suppress the harmonics from your transmitter, pi L is one way to do that. And then the frequency response of a T network, here we go with a T network, with series capacitors. That's our high jump or high pass case. This is going to be a high pass filter or network. So I hope you can see how those goofy little memory tricks that I shared will help you with these pool questions. Otherwise it gets really confusing. And right on to some questions. Okay, and here's your memory test. We're going to see if you captured that concept. How are the capacitors and inductors of a low pass pi network arranged between the network's input and output? A little bit of reading to do there.
delta,
It is delta. Capacitor connected between the input and ground, another capacitor connected between the output and ground, and an inductor is connected between the input and output, making it a low-pass filter, the inductor. And I go under the limbo bar. What is the frequency response of a T network with series capacitors and a shunt inductor? Same memory trick will solve this for you. High pass, right. Capacitor, hurdles, jumping over it, high pass. What is the purpose of adding an inductor to a pi network to create a pi L network?
alpha, alpha.
Greater harmonic suppression. See how easy this is?
Yeah.
Everybody's saying, yeah, right. Okay, how does an impedance matching circuit transform a complex impedance into a resistive impedance? All right, this one might take a little thinking. We did mention it, but didn't dwell on it.
Charlie.
It is Charlie. It cancels the reactive part. Remember with complex impedances, you've got 3 plus J7, so it cancels out the J part, cancels the reactive part of the impedance, and changes the resistive part into the desired values. It all has to do with the ratio of the inductive and capacitive reactance in the filter or matching network, which describes a pi L network.
Baker.
It's a pi network with an additional output series inductor. And into our last section for the evening. We're right on target time-wise, so you might actually get out on time. In fact, if we get to 8:30, we'll quit anyway, because Gary will throw me down the stairs. We're on the second floor, so that's dangerous. I don't want to be thrown down the stairs. So there's 2 flavors of voltage regulator types that are talked about in our chapter. We've got the shunt regulator, and we've got the series pass regulator. In the context here, let's consider this as being something that's feeding a 100-watt transceiver. That'll make it a little easier to relate to here. So this, of course, is highly simplified.
That'd be a really big center diode.
Well, yeah, and Kessler's material, he says that, and he's right, for this to work with a 100-watt transceiver, we're talking about a transceiver needing about 25 amps. There is no such thing as a Zener diode that can handle that much power. So this is in very low power applications or in receiver circuits, if you need some regulated voltage, you might see this, but generally speaking, in any kind of a power supply for a transceiver, you will never see this, because Zeners they can't handle it. This you see all the time though, series pass, okay, and in this case we have a reference established by the Zener diode that will hold the voltage output constant for varying levels of load drawn by the transceiver. Transceiver might only draw an amp or so and receive. It might be drawing 23 amps in transmit at 100 watts. So this circuit has to hold that voltage at 13.8 over that wide current range. So here's our shunt regulator. There's just one pool question, and it operates by loading the unregulated voltage source. So we've got this current flowing through the Zener diode at all times. So it's not very efficient. So that will cause this to stay at 13.8 volts no matter what current is being drawn over here, if this is big enough and the resistor is small enough. So the key to remember is that the blue text here. Maximum current flows all the time, very inefficient. Power not used by the load is wasted in heat over here. So just this one fact. So you need to know about the shunt regulator. Everything else is going to be about the series pass voltage regulator. All right, so how does it work? Pool question on that. says the conduction of a control element is varied to maintain a constant output voltage. Well, the control element is the transistor, and how hard that transistor is turned on, how hard it conducts, will cause different load outputs, different levels of current to supply the transceiver, holding the voltage at 13.8 the whole time. So Q1, also called a pass transistor, controls the current to keep the voltage output constant. Pass transistor maintains constant voltage over a wide range of load current. And the Zener diode is used as a voltage reference to compare that output with and turn the transistor on or more left. Notice they got a whole mess of pool questions out of this one circuit. Give you a second to review that. Okay, a second's up. Okay, linear voltage regulator. And they refer to this in another whole pile of pool questions. Okay, first of all, what is this thing? The circuit shown is a linear voltage regulator. Here we go. And as we said, Q1 controls the current supplied to the load to keep the output voltage constant. So here's the load, our transceiver in this case. We've got the input. I don't know what they typically run, but in this case it's 25 volts DC. And then the pass element will step that down to what the 13.8 that the radio needs. C1 over here is a filter capacitor. It filters the output of the power supply, so you're putting fairly clean voltage into the circuit. C2 bypasses the rectifier output ripple. So here's C2. And you'll notice that the base of the transistor is going to be able to see any ripple that's in the power supply. So we don't want to be modulating this output. We don't want to be modulating the voltage and current output of the circuit with any hum that might be in the output of the power supply. So that's why that's there. C2, or that's why this is here. C2 bypasses the rectifier output ripple around D1. So D1 can stay pure. C3 prevents self-oscillation. R1 supplies current to D1. R2 provides minimum load over here. So when the transceiver is not connected, the circuit will be able to keep functioning. And then D1 is the Zener diode, which provides a stable voltage reference to hold this at, well, we're talking a transceiver context, it'd be 13.8 volts typically. So, a minute to review the blue text. Now, a voltage regulator can be really small. If you only have to regulate a voltage over a small current range, you can get these devices. This is probably a 7805. I can't quite read what it says there, but that's a typical number for a low current 3-terminal voltage regulator. A 3-terminal voltage regulator is a series regulator. We've got highly simplified, you've got, I don't know which pin is which, but we've got the output of the power supply over here, we've got the output that goes to the transceiver over here, and then this is what would control it. So here we kind of see those 3 terminals, input, output, and reference voltage. Now, this is a concept that's going to take us back to our technician training. They ask, secondly, the first thing, dropout voltage is minimum input to output voltage required to maintain regulation. So we've got 25 volts here, we want 13.8 here. If the power supply voltage keeps getting lower and lower and lower, eventually this is not going to be able to pass the voltage that we need. So that the definition of dropout voltage is we have to maintain something that's higher on this side than what we're putting out, and when we no longer can do that, that's when the circuit drops out. Minimum input to output voltage required to maintain regulation or maintain the 13.8. Okay, now here's the tricky one. It'll take us back to our technician math. Now the formula for calculating power dissipated by a series linear voltage regulator. Well, think for a minute why we would be concerned with the power being consumed by the pass transistor. And remember, it might be passing as much as 20, 23, 25 amps to the transceiver. So at some point, this device could get really hot. So the concept of how much power it's consuming could be very important. So for calculating that, it's the voltage difference from input to output. So we got 25 volts over here, and I'm saying 13 volts over here. Remember the pi formula, power equals current times voltage. In this case, with the numbers I've shown in red, 13 volts times 2 amps is 26 watts. So this transistor is going to have to dissipate 26 watts running at that current level. Quite a bit more than that at 20 amps. So it's the voltage difference from input to output multiplied by the output current. And so if you can picture it this way, you'll get this. Then battery operating time. This was new in this pool. So a battery, and here's a biennial battery. This is what I use for POTA and soda. Carry one of these. It's a lithium iron phosphate battery. And they're rated in amp hours. Well, what in the world does that mean? Okay, well, a 12 amp hour battery can supply 1 amp for 12 hours, at least in theory, and then it'll be fully depleted. The nice thing about LiFePO batteries is they hold their voltage almost constant until they're getting right close to full discharge. So if you can get the idea that it's the amp hour rating of the battery divided by the current that you're using, give you the number of hours of operation. So then here it is in the context of the pool. Thus, battery operating time is calculated by the capacity in amp hours divided by the average current that's being used. It'll tell you how long the battery will last. It's a little hard to calculate because if you're using it for parks on the air activation, for example, sometimes you're transmitting, sometimes you're receiving, so you can't calculate that precisely because you don't know what the transmit versus receive ratio is, but this is how it's done. Now we're going to talk about switch mode power supplies. So here's a little one, here's a great big one. PowerWorks supply, 13.8 volts at 30 amps. It weighs a whopping 3 pounds. Here's an Astron, it's a 35 amp. It weighs 30 pounds. So this weighs 10 times as much as this one. This is a switch mode supply, this is a linear supply. So how do these work? They work by varying the duty cycle of pulses to a filter, the switch mode power supply. I'll show you a diagram in a minute. The pulse duty cycle is controlled by feedback from the output voltage, which then holds the output voltage constant. So if you're transmitting, for example, you're going to need a lot more current. It'll sense that the voltage is going down. It'll give wider pulses through the circuit to hold that voltage up. Less expensive and less weight, again, switch mode power supplies. The high frequency inverter design uses much smaller transformers and filter components for an equivalent power output. This is running at 60 cycles AC, requires much bigger transformers to be effective at that low AC frequency. These can be running at tens of kilohertz. So much smaller transformers and filter parts. And here's an interesting one. This is why you have to make sure if you're going to get a switcher, a switch mode power supply for your ham transceiver, you want to get it from a ham radio, somebody that's designed it for ham radio use. Because switch mode, we're actually chopping up the AC signal as it's coming off the line. We're talking square waves, all kinds of harmonics. They can be very noisy. So switch mode power supplies may generate interference that appears as a series of carriers at regular intervals across a frequency range. So if you tune into whatever band you want, say 40 meters, and you see that there's spikes all up and down the band, evenly spaced, that might be garbage coming from your switching power supply. So,
And people don't think about, and we're talking about ham radio power supplies
Yes.
here,
Yep.
but the little cubes that you're powering your cell phone, that's a switch mode power supply.
Mm-hmm.
So those little power cubes are really RFI generators.
Yep. Yeah, the little cubes that run your cell phones and all kinds of other electronics, yeah, they can be horrible. They can really be horrible. All kinds of stories we could share there. So these are things you need to know. Now, why would a ham ever not want to use a linear supply? Well, they cost a lot more. They're much heavier. But some hams insist that they'll only use a linear power supply with their equipment. But modern ham power supplies are quiet. I've got both, use them both. These are much cheaper, probably $120 for this one. I don't know what an Astron 35 amp supply is now. It's probably around $350 expensive. Here's a little picture of how they work. Input, rectifier, and filter. This happens right at the mains input of your right off the wall. It's chopped up. There's an output transformer, rectifier and filter, and DC output, and then there's a feedback loop here that comes back. If the voltage is too low or too high, depending upon the load, it will adjust the pulse width of the inverter chopper to bring the DC output up to what you want. So here's an article if you want to know more. And then we'll get into high voltage supplies. Now these are supplies that would be powering a high power amplifier. For example, you got a 1500 watt tube type amplifier, that would take a high voltage power supply, probably several thousand volts. Now the capacitors used to filter the output, sometimes it's hard to get capacitors that are rated in that high a voltage. So you can put several capacitors in series that are within the range. So if you're connecting resistors across series capacitors in the output, that serves to equalize the voltage drop across each capacitor. So the capacitors are rated at 350 volts. You want to make sure that you don't have more than that on one and less on another one. And these resistors will help equalize that. Resistors in parallel will also discharge the capacitors when the voltage is removed. You still always want to discharge any high voltage capacitors if you're ever working on one of these power supplies before you work on it. And you want to provide a minimum load on the supply. So this is what those resistors do across the output capacitors. There's another concept here called a step-start circuit. When you first turn on your power supply for a high power amplifier, you'll draw a lot of current as those capacitors charge. So if you can start it with a lower voltage, and then when those capacitors are charged up to that lower voltage, then you switch to bring it up to the full voltage, you don't have that huge inrush current that can damage things. Got a diagram here. So here we've got 1,000 volts DC. Battery? No, it would be transformer rectifier of some kind over here. But you get the idea, DC source. And if our capacitors, you always want your capacitors to be rated higher than what the minimum is. But if this is working the way it's supposed to be, and you've got these resistors in parallel, they should be dropping 1/3 of the supply voltage. So that would only put 333 volts across each capacitor. So you'd probably have 400 volt rated capacitors in this case. But this is the concept. And then you can see that you've got a constant load here. When you turn off the supply, these resistors would discharge the capacitors and provide a small load if nothing was going on. And then the step-start circuit we mentioned allows filter capacitors to charge gradually. So here we've got a relay. It would be some kind of a timing circuit here. So when you first turn on your power supply, this would be open. So you might get just a certain percentage of the output voltage out of the supply. Maybe a second or two later, the relay would pull in, short out this resistor, and then you'd get the full output, the full input to the transformer, the full output out of the power supply. So that's the concept of a step-start circuit. And on to some questions. I think this will wrap us up for the night. How does a linear electronic voltage regulator work? now we're jumping back. We talked about some things in between.
delta,
It is delta. Conduction of a control element or a pass transistor, as we discussed, is varied to maintain a constant output voltage. What device is used as a stable voltage reference?
Alpha.
Alpha, the Zener diode. Yep. Which of the following describes a three-terminal voltage regulator?
Bravo.
It is Bravo. It's a series regulator, but it would be set for a regulator for a fairly low amount of current output. A little three-terminal small transistor-sized package wouldn't be able to handle a transceiver. Which of the following calculates power dissipated by a series linear voltage regulator? This one you might have to think about. Remember your Ohm's law.
Charlie.
It is Charlie. Voltage difference from input to output multiplied by the output current. Power equals, that's the pi formula, power equals current times voltage. Good, that's it. Which of the following types of linear voltage regulator operates by loading the unregulated voltage source? This was the one and only pull question for this type of regulator.
Delta.
It was delta, the shunt regulator, correct? All right, so some questions about linear voltage regulators. What is the purpose of Q1? It's this thing right here. Some tempting answers in there that are wrong.
Delta. Charlie.
Charlie, it is, yeah.
Charlie.
Controls the current to keep the output voltage constant. Yeah, the switching and chopping, that applies to a switch mode power supply. This is a linear voltage regulator. What is the purpose of C2? Did I, I gave you the answer. You better figure that one out.
You're
Purpose.
gonna do that in the exam too, right?
Yeah, right, yeah. They'll fill in the little box for you. Well, C2 is in parallel with D1, so it bypasses the output ripple, if there's any left over around D1, so that it doesn't modulate the output with it. Yep. Okay, this time I'll be more careful and not give you the answer yet. What type of circuit is shown in figure E7-2?
Charlie,
Charlie.
Yeah, that's kind of a gimme, but it's in the pool, so we got to do it. What is the dropout voltage of a linear voltage regulator?
Charlie.
Yeah, that is Charlie. That might, you've got to kind of think through that one, but that's correct, Charlie. How is battery operating time calculated? I can hear the wheels turning.
One of them got time constants in it.
Charlie,
It is Charlie. Capacity in amp hours divided by the average current. So a 12 amp hour battery drawing 1 amp will last for 12 hours. The amp hour rating of the battery divided by the current being drawn from it. How does a switch mode voltage regulator work?
Bravo.
Right, by varying the duty cycle of pulses to the input filter. It senses when the output voltage is going down and gives wider pulses to provide more current. Why is a switching type power supply less expensive and lighter than the equivalent linear power supply?
A
Charlie,
smaller transformer.
We sure like Charlie tonight, don't we? Hi, Charlie.
we do.
Yeah.
Hi, me.
The high frequency inverter design uses much smaller transformers and filter components for an equivalent power output. And that's because they're running at much higher internal frequencies. What causes interference received?
All
Did I write
works.
this right? Yeah. What causes interference received as a series of carriers at regular intervals across a wide frequency range?
Alpha.
Alpha.
Yeah, that would be a really cheap switch mode power supply. Some people try to use computer supplies out of older computers, and they tend to have this issue as well. If a power supply is designed for ham radio use, it's probably pretty clean. What is the purpose of connecting equal value resistors across power supply filter capacitors connected in series? Read carefully.
All of the above.
Yeah, it is all of the above. I heard somebody start to say alpha. Alpha is true, but so is Bravo and Charlie, so it's all of these choices. What is the purpose of a step start circuit in a high voltage power supply?
Delta. Delta.
Yes, allow the filter capacitors to charge gradually. Correct. All right, the next slide you're going to really, really like, okay? I promise. It's the end of Chapter 6, Part 2, Radio Circuits and Systems. We covered a lot of stuff last week and this week. Keep reviewing it. Take the chapter review at the RRL site and keep this stuff fresh, because there was a lot of stuff there. So what do we do now, Gary?
Well, we could, you want to go to super source, please?
I have a question for you, Dave.
Sure.
Mike?
When you put a automatic antenna tuner in line, do you put that before the SWR meter or in line with it?
That is a really interesting question, because the answer is it depends upon where you want to be reading the SWR. If the antenna tuner is doing its job correctly, if you put the SWR meter between the transmitter and the antenna tuner, and the antenna tuner has tuned correctly, you should have close to 1 to 1, or certainly less than 1.5 to 1. The output side, though, of the tuner is going to be the difference between the impedance of the transmitter and the antenna itself. So you'll usually see a higher SWR over there. In my station, I actually monitor it on both sides just to see what's happening. I want to make sure the transmitter is happy, and I want to have an idea how close to resonant I am on the antenna. So long answer for a short question, but it'll be different on either side of the antenna tuner.
And there can be permutations. That automatic antenna tuner, if it's in your shack, that's kind of what we're talking about.
Yes.
But if the antenna tuner is at the base of, let's say, a 43-foot vertical out in the middle of a field, well, that's going to provide impedance matching at that point, and it should be 1 to 1 all the way on the transmission line coming back into your shack.
Right.
So.
Depends upon where you're measuring it. Yep, that was a good question, though.
Well, I've got a topic.
Okay.
6 meters. And up in Alaska, Snowkeeper, listen, we need you to be operating on 6 meters, please, because the band is magic right now. We're at the top of the 11-year sunspot cycle, and making contacts on FT8 and whatnot is just amazing. So here I am in the upstate of South Carolina with a modest antenna system running about 250 watts. I made an FT8 contact to India the other day on 6 meters.
Wow.
So
Yep.
the DX is there. We need more people to be on 6 meters, please, so we can make some more contacts.
It's worth buying an antenna. If your transceiver will do 6 meters, 6 meter 3-element beams aren't very expensive, and you don't have to have them up very high. 15 or 20 feet will be fine. You want to be a quarter of a wavelength
It's
above
the
ground.
magic band. When it's
Yep.
magically open,
Yep.
you don't need much.
Yeah, if you've got a transceiver that does 6 meters, it's not very hard to get on 6. A modest antenna.
50.313 megahertz. That's the FT8,
The FT8
frequency for
frequency,
6 meters.
yeah. Good. Anything else? Questions? Ham radio stuff? We're ending just a little early tonight, which I'm surprised. I thought we'd need 2 hours and cramming.
Well, I'll
but-
take the 2 hours next week because we're going to be talking about radio measurements and signals. Oh man, there's a lot of stuff there. So have a wonderful weekend coming up, but set aside some time so you can read the upcoming chapter.
Yep, lot of stuff there. All right, well, we'll say good night, 73, and thank you for hanging in there. You all did really well.
73, y'all.
Did really well.
Hi, guys.
Thank you.
You bet.